Good morning, good afternoon, good evening. Thank you everyone for joining our day 4 of the 3-month hands-on certification program in Pharmacometrics and PK/PD modeling using RS and LME. So today we have Dr. Gozi back with us, and we would be going over the homework assignment questions. And I do understand and appreciate that this homework assignment really made you think. And also that not having access to a software tool or like really teaching you a software tool yet, this focus of this assignment was primarily for you to understand the concepts and understand the theory behind before you start using a tool. And again, welcome back to your day 4. For all of those who tried to work on the assignments and completed them, kudos to you, congratulations. And for those who tried, great work. Again, it's not about whether you get the answer correct or not. This is primarily for you to have the approach that you can solve the questions. And of course, we will go over the assignments as well. And I know that in some cases we have given you some extra time. You know, love to get your feedback as well. I know some of you have reached out because things were tough. Again, thank you for trying. So Dr. Gozi is back with us today. He will go over all those questions, and looking forward to spending another great day with you guys today. I'm going to stop sharing my screen now, and Dr. Gozi is going to take over.
Okay, very good.
Thank you, Serge.
Okay, it's my pleasure. Let me see. Share. Let's see. Yes, I think that you can see my screen. Yes.
Yes, we can see your screen, Serge.
Okay. You can hear me. Okay. Then again, as Aruna mentions, I mean, the goal of the homework was not to scare you, but just to try to see if you can think about how to understand the concept and apply the concept in trying to answer the question. And maybe the question were a little bit tricky, and that's okay. I mean, I had 2 options: either just to ask you very simple questions that you know you can do in 5 minutes, or just thinking a little about that. And again, don't be worried if it was difficult. I'm going to explain everything now. I'm not going to solve the problem, but I'm going to explain the concept beyond the question, because there were some tricks, but that's okay. Then the first homework, we have 3 sets of homework: one for categorical response, one for count data, and one for time to event. Okay. Then again, what is a categorical response? A categorical response, you know, the usual example. It's for example, a pain model. A patient can feel good when they take the medication. Sometimes they can feel less good with time, and sometimes really bad. And then sometimes they really can feel very, very bad. And then you define for each of these category. For example, you put 4 category: 0, which is completely arbitrary. You say, okay, no pain; 1, a little bit pain, mild; and then 2, you say that it's moderate; and 3, it's severe. And again, it's completely arbitrary, the numbers. Now in Phoenix, and also in RS and LME, because apparently in our families they understand that almost everything is the same in Phoenix and in RS and LME. Just how to get into that, it's a little bit different. But I think that the rules will be the same, which means that when you have categorical response, you will have a data set, and the data set will have the value 0, 1, 2, 3, or any integer. Now, what's the problem here? We have a one compartment model with a combined bolus and infusion. Now, I mean, the combination of bolus and infusion is standard in many trials, and all the ideas that you want to do infusion, but when you put an infusion, it takes some time to reach steady state. And one of the things that we commonly do, it's just you add on top of the infusion at the beginning at t equals 0, you put a big bolus. And all the idea is that you want to try to reach steady state very fast. The trick here is not really a trick, but this is in mathematics, you can do things that you cannot do really in real life. You can just adjust the bolus in such a way that you are going to reach steady state immediately. And then let's look together if basically that's the case here. Then we have just 3 patient data. If you want, we are talking about 3 average set of PK data. We have 3 dosing, 100, 1,000, and 10,000. That's basically the infusion. 100, 1,000, 1,000, and 10,000. And we have a model with a categorical model with 3 levels that I call 0, 1, and 2. 0, for example, for no side effect, 1 for mild, and 2 for severe side effect. And again, we are talking about categorical response, and the categorical response is linked to my PK model. Then we are talking about PK-PD relationship, where the PD is not the standard PK that it's continuous, but the PD is itself a set of categories that are, at each time the patient can have one of the 3 categories. Then the difference between continuous response and non-continuous response is that once you are talking about categorical response, instead of putting an equation like a PK equation that gives you basically the category itself, you cannot do that. You need to define a probabilistic model that links the level to exposure. Then you need, if you remember, we learned together that if I have 3 levels, in order to solve the problem, I need to define basically the probability. I need to define a model for the probability to get the highest level, which is 2, and a probabilistical model that give me the probability to get the level 2 or the level 1. This is called the cumulative approach. Now, because probability must be between 0 and 1, we need to use a transformation, and this is called the logit transformation. Or if you want the probability to be level 2, can be expressed as the I logit, and the I logit, if you remember what I told you about the I logit, I can write it here. It's a I logit of x is equal to e to the x divided by 1 plus e to the x. Then basically, when you have x going from minus infinity to plus infinity, then the I logit x will go from 0 to 1, which is basically the idea here. Then when I'm putting an I logit operator here, and inside I put whatever expression that I want, I know that the probability always will go between 0 and 1. Then here, I use a simple model where I have I logit of a plus b multiplied by c divided by c plus c50. If you want, it's like an Emacs model, but in the logit domain, okay? Then a is called the intercept in the logit domain, and b, if you want, is the slope, except that instead of multiplying this by c, you multiply this by c divided by c plus c50, which means that you have a saturation. Then if you want, it's a probabilistic model that uses saturable expression, but in the logit domain. And whatever we have here, what I know about here is that if I have a saturation, it means that depending on EC50, I will not be able always to reach basically the larger probability value because I can have saturation. And this is basically my model. Now, the effect of the drug is to increase the side effect. And how can you see that? It's basically, if you look at the A plus B, and apparently I gave you also, let me see, you see, I gave you basically the value of A and B. You can see that A, B, and D are positive. Then what does that mean? Always you need, if you know, if I'm, let's look first at A, B, and D here, okay? If I look at A and B, then in the logit domain, A is positive, which is not really important because even if it was negative, it doesn't change anything. If you look at the slope, if the slope is positive, what does that mean? It means that when the concentration increases, then B multiplied by the concentration increase. And if the I logit basically of something that increased, the I logit of something that's going up is going to give me also a probability value that's going up. In other words, when B is positive, it means that when the concentration increase, the probability to get a side effect that's severe increase. And based on the equation and the value of A and B, now you know that basically we are talking about the effect of the drug is to increase the probability to be in level 2, okay? Then that's why I put the effect of the drug is to increase the side effect. Now, if you look at the regimen here, we have 3 dose levels, and that's the average data, and that's the dosing information. Then what's happening for the first cohort at time equals 0? You give basically, you start an infusion. You are going to give 100, I think it's microgram, doesn't matter, whatever I told you. And the duration is 100 hours. But at the same time, you give also a bolus of 1 microgram. Then you have a combination of bolus and infusion. You know the standard practice in pharmacometrics is to assume that the bolus is immediate, which means that when I'm giving a t equals 0 bolus, okay, of 1, then my concentration immediately will be equal to the dose divided by the volume of distribution. That's the effect of a bolus. On the other hand, when you give an infusion at t equals 0, and you are going to give 100 microgram in 100 hours, at t equals 0, there's still nothing because you just start the infusion. Then at t equals 0, if there was a lean infusion, the concentration still would be 0. However, when you put a bolus, immediately this is going to give my concentration at t equals 0 not equal to 0, but it's equal to the dose divided by the volume, whatever is the volume, and I gave you the volume. And now let's just try to understand what we have here. Each patient ID equal 1, 2, and 3 got at time equals 0 both a single bolus as well as a 100-hour infusion. A1 is the dose input in microgram. In an LME, A1 is both the dose input as well as the amount at each time. That's just something that you're going to see when you're going to use the model. For example, patient gets a bolus of 1 microgram combined with 100 microgram dose given over 100 hours of infusion, both starting at time equals 0. And then again, when I'm talking about the second cohort, is getting a bolus of 10, then you can know immediately what will be the concentration at t equals 0. And then you start at the same time an infusion that at the end you are going to give an infusion of a total of 1,000 microgram, but that it will be done, it will be given over a duration of 100 hours. Okay, don't pay attention to the number because I know it's not really rational to give an infusion of 100 hours, but that's okay. It's just numbers. And then the third cohort, it's basically to give a bolus of 100, and then you start at the same time an infusion over also 100 hours. And I gave you the data, okay? The PD data sets are attached. Now let's just look together at the model, okay? If I'm looking at a one compartment model where I have basically a combination of bolus and infusion, the differential equation will just show you the infusion. It will not give you inside the differential equation the effect of the bolus. The effect of the bolus, it's something that you need to tell, okay, what's happening at t equals 0. And instead, if really you have a bolus at t equals 0, the concentration is not equal to 0, but it's equal basically to the amount of the bolus that you give divided by the volume of distribution. Then the differential equation tell you basically, explain you the processes that happen at the same time that explain why we are going to see a specific profiles for each of the three cohorts. Then what goes in, it's the rate, okay? And again, the bolus, it's handled outside the differential equation because it affects only the initial condition. At t equals 0, we have basically C is equal to the dose divided, the bolus that you give divided by the volume. Then what goes in a one compartment model is basically the rate of infusion that will be available only for 100 hours. Then basically after 100 hours, that rate is equal to 0. And what goes out, it's a first order clearance rate, then it's minus clearance multiplied by the predicted concentration in the central compartment. And C is in microgram per liter, okay? And then I gave you the parameters. And I have no random effect. We assume that we do not have any random effect. That's very important because, again, because we do not use the software, I could not put in the data random effect because then I cannot answer any question. Then the volume is equal to 1 liter. The clearance is equal to 1 liter per hour. And then basically A is 0.3. There's no units. And A not available, not actual or whatever. B, D, and EC50. And again, A, B, D, and EC50 are called the PD parameter that are linked to the probability to get level 2 and the probability to get level 2 or 1. Okay. Now, the first question, and again, I'm not going to give you all the answer, but I'm going to give you almost all the answer. Can you calculate the steady state concentration value for ID equal 1, 2, and 3 during the dose input first 100 hours? What is the time at which we reach steady state? Okay. Then the question is basically, let's just take the first cohort together, okay? Then the first cohort, you got a dose of 100, okay? For duration of 100. Then what is the rate during the infusion? The rate by definition is equal to basically amount per unit of time, which is basically the dose divided by the duration, which is equal to 1. Then basically, then I know that as long as I have an infusion, which is the question here, I know that the rate is equal to 1. And I can put 1 here, okay? Now, at t equals 0, what's happened with the concentration? I know that at t equals 0, the only impact on the concentration will be the bolus. And again, I'm not giving you all the answer, but you are going to understand what's happening. Then basically what's happening is that the concentration at t equals 0 is not 0 because I'm giving a bolus. Then it's equal to the amount, the bolus amount, which is 1 divided by the volume of distribution. And the volume of distribution is also 1. Then what's the concentration at t equals 0? It's in fact, it's equal to 1. And what's the clearance? The clearance is also equal to 1. Then what's happening is that because the rate is equal to 1, that the concentration is equal to 1, and the clearance is equal to 1, I'm getting basically 1 minus 1, which is equal to 0. Then what happened here? It happened here is that because we set up the infusion in such a way that the infusion rate will be equal exactly to the rate at which the drug is eliminated. Then, in other words, when what goes in is equal to goes out, we say that you reach steady state. Or in other words, and now I'll give you almost all the answer, we reach steady state immediately because we succeeded to add a bolus in such a way that you are going to adjust the input and the output to exactly the same rate. Then that was basically, can you calculate the steady state concentration? I just gave you basically the answer. Is that basically you start at the concentration of 1, you are going to stay at 1 all the time because you reach steady state. Then again, the answer to that question is that you reach steady state immediately. And as long as you have the infusion for 100 hours, what will happen is that the concentration will be constant because you reach steady state, which is that what's the definition of steady state? It's that basically in equal out, and whatever concentration you have, it doesn't change as long as the infusion is not stopped. Then this is make our life easier, is because now I know exactly what will be the level for the first cohort. Do the same thing for the second cohort and the third cohort. Then basically now you know everything. Based on the probabilistic model, what is the probability, what is the calculated probability of time for level 0, 1, and 2? Now, the good thing is that I know what's the concentration for the first cohort. You are going to do the same thing for the second and third cohort. Then let's again look at the first cohort where I know that the concentration doesn't change as long as I have an infusion, which is basically the question, versus time for level 0, 1, and 2. And maybe to make your life easier, I'm just going to ask you just to write the equation based on that. And again, during the infusion, okay? During the infusion, which is for the 100 hours. Then I know that what is the probability to get level 2. I know what is A, I know what is B, I know what is C because during the infusion, C is not going to change, okay? And I'm not going to ask you what's happening when you stop the infusion because that's it will be too complicated. And again, focus only during the 100 first hours. Now C during the first 100 hours is constant. We just did it together. It's equal to 1. Then I know A, I know B, I know C, and I know EC50. Then the only thing that I need to do is just to do exponent, where my x is all this, divide by 1 plus exponent. This is basically my x. And then I will know exactly the probability to be in a level 2 during the first 100 hours. Now, if I want to know what's the probability to be in level 1, I know that the probability to be in level 1 is equal, basically, I can calculate that, is equal to P21, the probability to be in level 1 or 2, minus the probability to be in level 2, because P21 minus P2, the 2 cancel, and you are left with the 1. And because I know A, B, and D, and C, and C50, I can know what is P21. Once I know what is P21, I can do P21 minus P2, and I'm getting the P1. And if you want to know what is the probability to be in level 0 during the infusion, then it's just equal to 1 minus the probability to be in level 1 or 2. And that's basically how you can do that with the 3 cohorts. Again, always first 100 hours for everything, okay? Based on the probabilistic model, what is the calculated probability versus time for during the first 100 hours again? Level 0, 1, and 2. And again, because nothing changed, the probability will be the same all the time during the first 100 hours. Again, I repeat myself, during the first 100 hours, A is constant, B is constant, D is constant, EC50 is constant, CL is constant, V is constant, and the predictive concentration is constant. Everything is constant. Then during the first 100 hours, the probability to be in its level is not going to change. That was the question. Based on the probabilistic model, what is the calculated probability versus time for level 0, 1, and 2 during the first 100 hours? Calculate it based on the observed data. Calculate based on the what is the probability coefficient to get level 0, 1, and 2 without accounting for the time variable. Now here, the trick is that during the first 100 hours, it doesn't matter what's happened. the time is not relevant because the concentration and all the parameters do not change with time. Then now you can calculate based on the observed level the probability for each patient to get level 0, 1, and 2. We can do this even with Excel. You just take all your data and you look at basically all the data that you have, and you look at the proportion of 0, the proportion of 1, and the proportion of 2. And probability is nothing else than just proportion, and you can do that. And then you can see if you see a match between the predicted and observed probability, because if you did it right, you should see that the probability based on the observed data to get level 2, and again, you forget about the time, just look at the first 100 hours and look at the data. And then the probability based on the data, you look, okay, I have 0, 1, and 2. Okay, what's the proportion of patients that have level 2 based on observation for each cohort? And then you say, okay, that's my proportion. And then you say, okay, now based on the model, what's the proportion? What's the probability? Probability is proportion. What is the probability to get level 2? And then you should see a match. And then you do the same with 1, and you do the same with 0. And then I'm asking you, do you see a match between the predicted and observed probability? Then you need to see that. And then the last question, what the time variable, why it's not what? Why the time variable is not relevant to be accounted for? And that's already answered that question, is that during the infusion, everything is doing 100 hours infusion. Because nothing changed with time, then the time is not relevant during basically the first 100 hours. Then that's basically the homework for categorical response. Again, I do not expect everybody to do everything from the beginning to the end. My goal was just to just jungle a little bit with this equation, understand the concept. And once you are going to deal with RS and LME, and if you do research project that includes categorical response, then at least you will have this kind of background information that can help you. Then before I'm going to the next one, do we have questions? Any question?
I know some of you have tried to work on these questions. And if you had used a different approach, again, there is no right or wrong answer. If you have used a different approach to address the questions, please raise your hand. We can unmute you. So yeah, I've seen Nilesh has risen his hand. I'm going to unmute you now.
Hi, this is Nilesh. So I would just like to ask what happens after 100 hours. So does all A, B, and D are still constant and only the concentration is changing, or everything changes?
Only the concentration.
Yeah, okay.
But again, don't pay attention to what's happened after 100 hours. Okay. Just okay. But if you ask already the question, basically, after 100 hours, what's happening? You start at the steady state level, and then your drug is going to behave like a first order exponent decrease.
Yeah.
Whatever concentration you have, the only thing that it's left, you can, again, I always look mathematically. Once the infusion stops, then basically what you have here is that this disappears, right? Yeah. There's no rate anymore. And then you are left only with a first order elimination rate.
Okay. Yeah.
Then whatever amount you have at that time, then basically it's like a new bolus that you give, and that's it. Okay. And that's the idea. Okay. But during the infusion, you are at steady state all the time. Okay. And because you are at steady state all the time, then everything's constant. A, B, C, AC50. Once you stop the infusion, the only thing that's going to change is the C. Okay.
Yes, with infusion and steady state, the scenarios are quite straightforward. But when it comes to oral dosing, where the concentrations are going up and down with time, that is when.
Yeah, that's right. Because we didn't have a software and all this, I'm asking you only what's happening during the 100,000 infusion.
Yeah. Okay. Thank you.
You're welcome.
Anybody else? Any questions? I think we have a question in the chat box. Manish, do you want to raise your hand so we can unmute you? Yeah, Manish has raised his hand.
Okay.
Accept the prompt, Manish. Yeah, you should be able to talk now. Yeah.
Yeah, sir, I want to get, I have one query. Once we will get the two probable equation, probability equation, 2-1 and another condition, probability second condition. Then you expected the concentration X as infusion rate. X, that's the infusion rate, that one that is the infusion rate. Then you plotted the equation I log it X is equal to exponential X divided by 1 plus exponential X. Can you explain again, because I didn't get clearly how we can get this equation for predict the concentration?
I can barely hear you, but I see that you asked if I can explain it in the I log it stuff.
Yes,
right?
yes.
Okay.
Yes.
Okay, good. Then basically, the I log it, like you have exponential, you have logarithm, you have basically what's called an operator. Basically, it's if you want, it's a function. Then when you have I log it of something, you take the something which is X, and here the something is A plus B multiplied by C divided by EC plus C plus D, or A plus B multiplied by C divided by C plus EC50. Now let's just start with the probability to get in level 2. Okay, in that case, X is equal to A plus B multiplied by C divided by C plus EC50. Then basically in our case, if you are talking about P2, if you do not want to use the I log it expression, you can just put basically exponent and all this 1 2 1 2. Okay, you will pay attention. You will pay attention to the parentheses, and then basically 1 plus all this. That's exactly 1 plus. Sorry, 1 plus exponent, and I'm closing this and this. But that looks more complicated, basically. That's exactly the same thing. In other words, I could give you the probability to get level 2 is equal to exponent, and then basically the X, which is A plus B multiplied by C plus 50, divided by 1 plus, again, the same thing, exponent X. And now what's happening is that the probability to be level 2 always will be between 0 and 1, because exponent X divided by 1 plus exponent X, if X is highly negative, let's say minus 10,000, then basically exponent to minus 10,000 is going to 0, okay? And exponent to minus 1,000 is going to 0. Then when X is really negative, then we get basically 0. And now if you have X really larger than 0, let's say 10,000, then exponent 10,000, the one is not, it's basically not significant anymore compared to exponent 10,000. And then you get exponent 10,000 divided by exponent 10,000, and then you get 1. Then whatever you do, whatever you have, whatever is this X, it doesn't matter what it is. As long as if it's basically between minus infinity and plus infinity, then so the probability to be in level 2 always will be between 0 and 1. And that's why we are using this operator. Now, the second thing that we need to make sure is that the probability to be in level 1 and 2 must be larger than the probability to be in level 2. Then if I'm taking exactly the same expression here, and I'm adding on top of that a positive value, you can see that this is positive. See, this is positive. Because this is positive, then I know that the probability to be in level 2 or 1 will be always larger than the probability to be in level 2. These are the two conditions that must be respected all the time. Is that when you add in the cumulative probability, when you add a level, you have probability to level 2, that's called the marginal probability. P to 1 is the probability to be in level 2 or 1. And I know that it's larger than the probability to be in level 2 because I add a positive number, which is D. Then all the idea to use the I log it, it's to help you, is to, instead of writing something really complicated, which is this expression, I'm just writing the I log it. And I know that the I log it is just going to take whatever I have inside the I log it and just doing exponent that inside divided 1 plus exponent that inside. And that's what we are doing all the time. I mean, most of the time with probabilistical models to use the expression in the logit domain. Okay.
Thank you, Serge. Thank you, Serge. I got it clearly how we can plot this equation. Yeah.
Okay.
Thank you.
You're welcome. You're welcome. Anybody else? Okay, if there are no more questions about that homework, then let's just try to understand the next one, which is the count data. Then again, what's the difference between count data and categorical response? I gave you an example for categorical response. Pain level, no pain, mild, moderate, and severe. And then I associate it with each of the categorical levels, a number, 0, 1, 2, and 3, but the number is completely arbitrary. In categorical response, 1 plus 1 doesn't mean that it's equal to 2. 2 multiplied by 2 doesn't mean it's equal to 4. We cannot do this a simple calculation. On the other hand, when we have count data, like for example, counting the number of heart attacks that a person got in a month. Then some people got 1, some people got 2, some people got 3, some people got 4, hopefully not. In that case, when somebody got, let's say, 4 events, I know that 2 multiplied by 2 is equal to 4. Then count data, it looks really like continuous data, except that it must be an integer, but you can use the rules of additivity and multiplicativity and subtraction and everything you can do with count data. What you cannot do with categorical response, okay? Now, when we talk about the theory, and again, you have to go to the theoretical part that I've been working with you for the count data. If, for example, somebody got 5 heart attacks in a month, what triggered the heart attack? It's something that is hidden that we don't know exactly. And it's driven by what we call the hazard rate. The hazard rate is telling me every moment there's a certain probability to get a heart attack. The hazard rate is defined as the number of events per unit of time, the number of heart attack per unit of time, when basically the interval time is very, very small. Now, if I have a function, an expression for the hazard rate, and we learn that together, I know that I can integrate the hazard rate from 0 up to the time at which I'm looking how many count data I have. And I'm getting then what is called the cumulative number of events. The cumulative number of events is then associated with the mean of a Poisson distribution. And once you know the mean of the Poisson distribution, you compare the mean predicted by the model, and suppose that the mean is 4.5, and then you compare the 4.5 with basically what you really observed for that patient during the time interval that you are talking about. Here it was 5 heart attack. And then depending on the PK parameters and the corresponding predicted concentration, you can calculate the predicted average number of event, or if you want the average number of counts based on the model, and you can also compare that with the observed number of counts, and you can in fact calculate the probability that if the mean was 4.5, what would the probability to get basically 5 heart attacks? And that was basically the goal of this exercise, just to apply some formula. And again, I use the same trick, and I'm giving you that for the 3 examples, is because I don't have really a software that I can use and make your life easier by taking, again, the same kind of system where you are at steady state during the infusion. And I'm asking you only to deal with the infusion time. Then here we have exactly the same system with a 1 compartment model, okay, like before. And then during the infusion time, you will be always at steady state because you basically compensate with a bolus that will make you reaching steady state immediately. Then remember that V is constant, CL is constant, Emax is constant, EC50 is constant, and also the predicted concentration is constant. Now, what does that mean if the predicted concentration is constant for each cohort? Emax is constant, C is constant, EC50 is constant, then H is constant. Now, if H is constant, then what's the integral of a constant? And I think that I wrote down here, the trick here is the integral of a constant. If basically the integral from 0 to t of a constant dt is equal to the constant multiplied by the integral from 0 to t dt, which is the constant multiplied by t. What does that mean? It means that if, for example, my h, it's, let's say, 5 events per unit of time. Let's say 5 events per hour. Because it's constant, then how many events I'm going to accumulate after 10 hours is equal to basically 5 events per hour multiplied by 10. That's exactly the simplest way to explain what is an integral, where what I have inside the integral is a constant. What's happening in real life that makes things more complicated is that the hazard rate changes with time. When the hazard rate changes with time, you cannot just calculate easily the cumulative number of events, and then you have to really integrate. But here it's very easy because, again, everything is constant. Emax is constant, C is constant, EC50 is constant. Then you can calculate H for the 3 cohort, okay? And then once you know H, you can basically integrate, okay? And you have the data set here, the count data. The probability to get a specific, to get the observed number of counts that you have in your data set can be calculated if you know the mean of the Poisson distribution, and the lambda is the mean. And again, the mean, you can calculate it by integrating the hazard rate from 0 up to the time at which you look how many events the patient got. Then I gave you the data set and asked you to take the first replicate, rep equals 0, ID equal 1, 2, 3. Okay, you have many replicates. Actually, just look at the first replicate. Calculate the probability to have obtained the observed count data at the end of the fusion, 0, 3, and 9 for ID 1, 2, and 3, respectively. Then if you look at the data, you're going to see that you got 0, 3, and 9, okay? And now if you want to calculate the probability, you need basically to use that equation. Then what's the probability to get 0? What's the probability to get 3? What's the probability to get 9? And this depends on what you observed, K, which is 0, 3, and 9. And then you just need to calculate the mean of the Poisson. But the mean of the Poisson distribution, you can calculate it by just looking at when you observe the count. You calculate H. You can know H because you know C because you are steady state immediately. And then you multiply the H by the time interval that you're talking about, which is the time at which you observe the count. Then the answer is very easy. You can know what's the mean of the Poisson. It's basically H that you can calculate, multiplied by the time at which you recorded the number of counts. Then this will give you the lambda. You can see that's the lambda. You know K, it's 0.309. And then you just can calculate the probability to get basically that observation by just looking at that equation. And again, lambda is equal to H multiplied by the time at which you basically observe the count. And K factorial, it's the factorial of K. Okay, factorial of 9 is 9 multiplied by 8 multiplied by 7, etc. up to 1. Okay. Then once you understand that, then you can do basically the rest. Calculate the average observed number of counts stratified by the dosing strata. You can do this with Excel or whatever. It's just the descriptive statistics. Then compare the average obtained with the probability calculated above based only on the first replicate. What can you conclude? What you should expect is that the average number of counts that you are going to calculate should be quite similar to basically the mean of the Poisson distribution that basically you calculate, okay, the lambda. And then again, what's the rationale to believe that the parameter for the hazard rate, Emax, and C50 will affect what is in the data? It's the same question, is that basically you are going to see that when you apply the model, you can see that the predicted probability match with the calculated probability. And again, probability is proportional. Now, based on the model, would it be possible to get migraine attacks for placebo patient and explain? Okay, then let's just look this. What is placebo patient? Placebo patient, it's patient that basically got dummy drug, which means that C is equal to 0. Now, if C is equal to 0, then H is equal to E max multiplied by 0. And it's equal to 0. Then if the hazard rate is equal to 0, and if you integrate anything that is 0, then the cumulative hazard will be 0. Then it means that basically you can never get any number of migraine attacks because the integral of H is 0, and you get 0 all the time. Then based on the model, basically you are never going to get any attacks. And when you are going to use the model and you put H equals 0, you are going to see that you are going to get nothing. That was basically the idea. I mean, based on the model, when the hazard rate is 0 all the time, then basically you cannot get anything. Nothing can happen. And finally, can you plot a histogram for the observed count data stratified by the 3 dosing cohorts? Then again, so you look at your observation, and you can just, for the 3 cohorts, you can just plot the proportion of all the count that you have. That you can just use Excel or whatever software you want and just do an histogram. And using software of your choice, simulate 100 patients for each dose cohort. You really don't need to do that. I don't want you to start with the software stuff, and that's, yeah, we leave to do that. Then again, all the idea here was just basically to understand the link between hazard rate, integration of the hazard rate that will give you the Poisson mean, to be able then to calculate the probability to get any count data based on that expression. And because again, we have a special system where we are at steady state from the beginning up to the end of the infusion, we can really calculate easily all this probability. because the integration of the hazard rates, it's something that you can do manually. And again, the integration of the hazard rate is just done by multiply h with the constant by the time interval. Just try to do a little bit of that and I will be happy. Any question about that part?
Again, if you have questions, please raise your hand so we can unmute you.
Okay, if there are no questions, then let's go to the last set of questions. And again, don't be scary about all this. It's just that all the idea is for you to try to think and to play with that, with the equation. And once you are going to have a research question that includes categorical response, count out time to event, then maybe then you are going to take advantage of all what you learned from the homework. Okay. Let's just shift for the last one, which is basically a time to event. In the time to event, I give you from Wikipedia the definition of the Kaplan-Meier that allow you to estimate what is called survival distribution. Now we learned together what is a survival distribution. Now let's just try again not to be confused, and let's just try to separate the three kinds of non-continuous response that we are dealing with here. Categorical response, like pain level, it's 0, 1, 2. 0, 1, 2, it's completely arbitrary. 1 plus 1 is not equal to 2. And each level corresponding to a specific, basically, pain level, in that case, if it's pain. When we talk about count data, we're talking, for example, for heart attack, we count the number of heart attack over a time interval. And that's called count data. 2 plus 2 is equal to 4. 2 multiplied by 2 equals 4. The value as integer. In that case, we can calculate the probability to get a specific number of count over a specific time interval using basically the Poisson distribution. The Poisson distribution mean can be generated by taking the hazard rate and integrating the hazard rate from 0 up to the time at which you recorded the number of count that you got. That was count data. Now in time to event, the time to event where, and I'm talking about the time to event that where the patient, once he's getting a heart attack, is calling the physician, is telling us, I got a heart attack. Hopefully he's able to do that. Then in that case, we use an additional column, which is the sensor. And in the sensor column for that patient, once he's getting the heart attack and he's calling the physician, we are going to put a 1. That's basically, it means, okay, that's exactly the time at which he got the heart attack. In the time column, you just write the time at which he got the heart attack. And you will have two columns, the time column and also the sensor column. If over if over the entire period that is basically that you look at that patient, nothing happened, then at the end of the trial, you are going to put in the sensor column. In the sensor column, you're going to put a 0. It's called right sensor, which means that it didn't get yet the event. And in the time column, you are going basically to time to follow up. You are just going to write the time up to what time it was basically follow that patient, TFU. Now, the time to event, again, use the sensor column 1, the event occurred, 0 white sensor, the event did not occur yet, and would occur only in the future. Then if you finish the trial, and for example, person didn't get a heart attack, it doesn't mean that you will never get a heart attack. But when you basically observe that patient, nothing happened. The strategy to try to quantify basically time to event using a mathematical model is based on the same principle of hazard rate. In other words, like for count data, if you're talking about a heart attack, every second a patient can get a heart attack. And the hidden function that it's continuous that basically is related to the probability to get at any moment heart attack is called the hazard rate. Now the hazard rate here was a little bit different. It's H is equal to E0 multiplied by 1 minus I max multiplied by C plus C50. Then H is the number of events per unit of time, the number of heart attacks per unit of time. If you integrate H, you get the cumulative number of heart attacks, okay? But now, how we handle data that are time to events is a little bit different than count data. And in the theoretical session, I explained you that. I told you that you first integrate the hazard rate from 0 up to the time at which the patient called his physician and told, I got heart attack. This is called the cumulative number of events. And then I told you that there's an equation that allow you basically to calculate. There's an expression that allows you to calculate the survival distribution. I can write this. I can write here the expression. Basically, S is equal to exponent. Oh, sorry. No, I cannot write something here. Okay. Anyway. I think that you can see on my screen, then basically S is equal to exponent minus integral basically of the cumulative basically I will refer that. Cannot write this as an equation. I would like you to look at the time to event material that I send you, and I gave you the equation for the survival distribution. What is the survival? The survival distribution is the probability not to get an event from 0 to t. Okay, then look basically at the equation. There's an equation that I gave you. I don't know why I cannot do that. Okay. Then again, once you know H, then you can calculate basically the the cumulative hazard. Okay, and then you can calculate also the survival distribution. Okay, and please do that. I don't know why I cannot edit this. Okay, then here again, we have the same equation. Then you know now the trick. Basically, you have a system where we are at steady state during the infusion. Then basically, C is constant. C is constant. E0 is constant. Imax is constant. EC50 is constant. Then again, I know that H is constant. Then the integral of H is basically equal to H multiplied by the time that it took to get to the event. Now, the time, how much time it took for the patient to call the doctor and say, okay, I got a heart attack. Okay.
So
then
Serge,
yes.
Serge, sorry, this is Aruna here. I was just, I think the participants have not received this homework yet.
Ah, okay.
So
okay.
We can, you can maybe just go over the questions part, and then, we can give them, okay. Yeah, we can give them some time to go over this. I know maybe we will look into this and try to streamline how you're getting the homeworks as well. And maybe put all the homeworks in a folder so you have the access to it. So yeah, thank you for bringing it up, Ramya, that you have not received this homeworks yet.
Okay. Then I just will explain the question, and then I will give you a few days to think about it. And you can always send me an email during that time.
Yeah, thank you.
And basically, I want you just to remind you that okay. I just want you to come back basically. Okay, and you can see here basically. Okay, you see that's basically the survival distribution. Then it's basically the exponent of the integral from t equals 0 to t equals t of minus h dt. Okay, then you know h is a constant. Okay, and if you know that h is a constant, then h is going outside the integral, and then you can calculate the survival distribution. Okay, then what are the questions? Again, like before, we have basically two cohorts, and always like before, we are going to see that they are steady state and the concentration is constant. And then that's the model, like before. And I gave you all the equation. Then V and CL are the parameter linked to the PK, and I max EC50 and E0 are the parameter linked to the PD model. And then derive and plot the survival distribution curve for the two cohorts, 110,000. And what you will need to do is just to basically apply that equation. And again, H is constant, and that will be easy, okay? And then it's just an equation, it's a mathematical formula, then easily you can plot that. And what can you conclude about the difference between the two cohorts? And what you are going to see is that the two survival distribution will be different. And then you are going to tell me basically what's happening. Maybe one is faster than the other. What if it's faster? And the hint that I'm giving you is that everything is linked to basically this. You can see that the effect of the drug is to decrease the rate at which you are going to get a heart attack. Okay, because it's a minus here. And what does that mean? It means that when the concentration increases, then the drug is going to help to basically decrease the hazard rate. Okay, and then you are going to see that in the survival distribution, because the survival distribution tells you about the probability not to get heart attack. Okay, then when you give a drug, then the probability to not getting a heart attack will be different if you have a high dose or a low dose. Okay, then that's basically the question, just to applying the formula. And then what is the effect of the drug? I already answered about that. It's because here it decreases, the drug helps that case. Okay, then you are going to apply the equation. And here I want you basically to read basically the equation from the paper, and I just explain you is that the survival distribution, it's a mathematical function, and also that basically allow you to predict what will be the probability not to get an event with time. Now, when you have data, sometimes without a model, you can also plot an approximation of that survival distribution. And that's what I want you to do, is to go over basically the article that explaining what is a Kaplan-Meier. And what I explained here, it's a little bit intuitively what's happening, and I don't want to go through that because I want you first to go through the paper. The basic idea of probability is that when you want to know what's the probability to get, for example, an event, to get basically an event at a certain time, the probability to not getting an event at a certain time, you just need to look every time at every time basically you need. Let me give you an example here. Based on the Kaplan-Meier formula C attached above, estimate the survival probability based solely on the observed data for the two cohorts and superimpose those with the model-based survival distribution curves. Then what I want you to do is basically to look at the article and that explain you, okay, I have data and you have data. You have data, the TTA final data set. And when you look at the data, you need to do the following. You need first to stratify the data by the two cohorts. We have two cohorts, remember? We have the cohort, the low dose, and then you have the high dose. And the first thing that you need is to stratify data. It's like two different homework for the low dose and the high dose. Okay. And now the idea of the homework is, okay, can I just take the data and based on the data just calculate the probability not to get an event as a function of time, just based on the data, okay? And then I'll give you also a hint, not that patient 6 at time equal 100 when he finished the infusion was right sensor, which means that he still didn't get an event. Then the event didn't occur. It's just a hint, just pay attention to that. And here I just explain you basically all the steps that you will have to go through. But again, I want you first to go to that. Then I explain, start by filtering only the sensor data. Use Excel, for example. In other words, only from the data, the 0 and the 1. Remove the PK part if you want. Then split the data by the 2 cohorts. So the 2 separated data set by time. And that's what you will need to do. And then for each data set, start with the first time to event. The probability to survive is, of course, 1 at time equals 0, because when you start the process, everybody didn't get yet an event. And then what is explained in the Kaplan-Meier basically reference, it's hard to calculate every time the survival distribution at a specific time. And then the way it's working, you start with the first time to event. The probability to survive is, of course, 1, but must be multiplied by 1 minus the number of events, which is 1, because at each time you have 1 event, if you have 1 event, divided by the number of remaining patients before that time. If, for example, you have 60 patients, okay? And then at the first time to event, you see that basically you lost 1 patient. Then the probability to survive is equal to 1 minus the number of events, which is 1, divided by the number of remaining patients before that time, which is 60. And it will be 1 minus 1 divided by 60. Then you want to see what's the probability to survive up to the next time, where you look at the next time that you got an event. You go to the next time or event and multiply that probability, the one that you just compute, by 1 minus the number of events at that new time, divided by the number of remaining patients before that new time. Then again, you are going to multiply the previous probability, multiply by 1 minus, again, you got 1 event, if you have really 1 event at that time, divided by the number of remaining patients before that new time. Now, the number of remaining patients before that new time is not 60, because you lost 1 patient, then it's basically 59. And then you go to the next time, and again, you multiply by 1 minus, again, a new event, divided by the number of remaining patients before that time, which will be now 58. Then as long as you lose every time 1 patient, it will be, if you want, always the same equation, but one time you're going to use 1 minus 1 divided by 60, multiply by 1 minus 1 divided by 59, multiply 1 minus 1 divided by 58, etc. And the only trick that I'm not going to give you an answer, what's happened for that patient that was right sensor. In other words, you look at that time with right sensor and what's happening. The only difference is that the number of events at that new time is 0 because it didn't happen. Then at that time, you are going to multiply by 1 minus 0 something. And then in other words, you're just going to multiply by 1. And that was basically the trick. Now, when you're going to do that, and you should do that as a group and to play a little bit with that, what you are going to see is that you are going to get a survival distribution based on the Kaplan-Meier, that which should be quite similar to the predicted survival distribution that you got from the model. And that's the kind of goodness of fit that you do in Phoenix or in RNLME. I guess they will have also the Kaplan-Meier comparison that allow you to say, okay, I did a good job. It's because my predicted survival distribution matched well with the Kaplan-Meier based on just on the data. Again, you need, again, you didn't look at that list. I didn't know that. Then Arun, I will send you that homework again if you don't have it, and you can share this with the student. Then again, all the idea here is to do some brainstorming and try to working as a group and to learn, and not more than that. I do not expect everybody to really be able to understand everything at this stage. But again, once you are going to do research, the clinical endpoints most of the time are either categorical, count data, or time to event. That's really, it's happening all the time. Then I think that people that are going to do in the clinical that are going to be linked to clinical trials and the pharmacometrics and clinical trials. I think it's important to understand all that. And the PML has been developed when we worked on the development of the program, and I was a part of it for at least something like 8 years. Then everything has been done to be able to solve problems that include categorical time to event count data. Okay. Okay, Bim Bahadur Shodani, please ask your question. Resting. Aruna, can you give somebody rest?
Yeah, so please accept the prompt, Bim. Did we lose you?
I cannot hear you. I cannot hear
Hello?
anybody. Now, Aruna, I cannot hear. Aruna, I can hear you. Yeah.
By mistake, it raised me. Sorry.
Oh, okay. All right. So you don't have a question?
No.
Okay.
Sorry.
All right. Thank you, Bim.
Okay, now just pay attention that I'm asking you a lot, and I don't know if it's good or bad, but I prefer to ask more than ask less. If you do a little of what I asked, that was a lot, then that will be good enough. But again, Aruna, you can send my email to anybody that has any issue and that is interested. I think that you should try a little bit, and once you are going to practice this with the software, and maybe if you're students and you do research that involve this kind of response, then that's where you are going to basically enjoy all what I did with you. Obviously, this is really my expertise, all this kind of stuff.
Sure. Thank you, Serge. Again, wanted to check. I think there are a few things that are missing from our end as well. We have yet to post the day 3 video, which we should be doing soon. We had some technical difficulties on our end. So we should be having the day 2 and today's video also posted on the YouTube channel in the next day or so. And in terms of the homework assignments, we will create a folder and upload all the homework assignments in that location. So you should be able to get to them. Again, we are using different means to send you emails. Sometimes maybe the emails are ending up in the promotions in your inbox or in the spam folder. So I would request you to please keep an eye out. Also, you may have seen this email, and I know some of you have attended this. So Anna from Certara and the Certara group has scheduled time for you to attend a meeting and get one-on-one help for the installation of RS and LME. The meeting was yesterday, and will also, that was from 11 a.m. to 12 p.m. Eastern time. The same time next Thursday has been allotted for you to get help to do the RS and LME installation. I will reach out to Anna offline, and we will try to schedule maybe another time window as well. My understanding is that there were about 25 participants who attended the installation workshop yesterday. So which means just about a quarter of the participants have gotten the installation done. If needed, and please get back to us if the time doesn't work for you or if you need any additional help. We will support you in the process of getting the installation done. And I think there is a question here. Srinivas is asking a question.
Mm-hmm.
Srinivas, would you like to raise your hand and we can unmute you? If you cannot for any reason, then we can read the question. So you will have to raise your hand, Srinivas, because otherwise it is difficult for us to find you in 100+ participants.
Hello, am I audible?
Yes, Srinivas, go ahead.
Thank you, Aruna. Thank you very much. Thank you, Serge, for your detailed explanation on PKPD, particularly population pharmacokinetics. So actually, we have gone through the first assessments on likelihood as well as the PKPD assessments. So it would be great if we have a discussion on that two assessments, Aruna.
Discussion about what?
Likelihood assessments and PKPD, the day 2 homework.
I ask you not to go through that likelihood because it was not really trivial. I asked not to do the. I don't know if you heard about that.
Yeah, because a lot of confusions are there in the iterations and all. So the
yes,
PD
because but then forget about this likelihood. Basically, if the likelihood was just one patient, one observation, all the idea was at the beginning to say that the ratio of the likelihood is like the ratio of the probability. But once you start to integrate the likelihood, then it's not correct anymore. And the ratio of the global likelihood is not equal to basically the ratio of the probability. Then that's why I told Aruna and I told everybody just not to work on that because it's really way more complicated. Then forget about it.
Thank you.
Just remember only one thing in general, is that if the likelihood is really a probability, like in count data, if you have if you have only one data point for one patient, and you try to optimize that by some mean, then all that is just to remind you that if you put a parameter and you get a probability to get that value, it's equal to, let's say, 0.7, then obviously, if you do another parameter and the likelihood is 0.35, then the 0.7 is twice the 0.35. That was just all the idea. Then that when you have one observation for one patient and you calculate the likelihood, and then if the same patient you calculate the likelihood using a different set of parameter and you get double the likelihood, then it means that for the second set of parameter, the likelihood is twice better than for the first case. But once I start to understand that I have to integrate, then basically everything's falling apart and it's really more complicated than I saw. Just don't do it. Okay?
Thank you, sir. Thank you very much.
Yeah, welcome. You know, I invented all this homework. Then even when sometimes I invent something, and after the fact I pay attention, oh my God, no, we cannot really answer that. But other than that, I think that everything is okay, it's correct. By the way, all the exercise I test with Phoenix and LME to make sure that everything was correct. And then any other question?
So I quickly wanted to go over how we are doing in terms of how many people have submitted homework assignments and how we are doing overall. Krishna, if you can raise your hand, maybe I can unmute you because I know you have the latest stats.
I will stop sharing.
I don't see Krishna yet. So yeah, hi.
Yeah, I'm
Go ahead,
here.
Krishna. Yeah.
Yeah, for day one, around 70 participants have submitted the homework assignments. And for day two, which is now like clubbed with the other two assignments. So around, around 30 of them. Sorry, yeah, 30 have submitted.
Sure. So again, for all of you, I would strongly encourage you to submit your homework assignments, as you're aware that in order for you to be eligible for getting the certificate at the end of the workshop, you would have to submit all your assignments or answers to the assignments. And also you will have to participate in all the workshops. I do understand that there may be times that you have technical issues, either because of internet connections or others. That is also the reason why we record the workshops. So do keep in touch with your groups, do work on addressing or working on the homework assignments, and reach out to us if you have questions or any issues. We are committed for your growth and knowledge sharing. So we would love to support you in the process. So do continue to work on the homework assignments. And I know we have had, again, these are, we have close to 100 participants. So this is beyond the capacity for us also to, so there may be a few things that may get lost because of the numbers that we are dealing with. So please be patient with us. Overall, I know that some of you may not have received homeworks, either because the email has not reached you. We will actually share the link where you can find the homework assignments as well as the slide deck. And we will also share with you our YouTube channel where you can find the video recordings. And if you have any questions, please do write back to us. We will try to resolve your questions. I know we also had made a request that the participants have to pay a nominal fee. We would like to make sure that all the participants who have been asked to pay have made their payments. And for some reason, if you have technical issues or are unable to make the payment, please get back to us. Any other questions that anybody has in terms of the homework assignments or first, I think we want to focus more on the homework assignments and other teaching related stuff. We will address the technical issues later. If you have any questions, you can raise your hand, we can unmute you. If not, you can post your questions on the chat. Both of them work. I don't see any movement, so I'm assuming that you have everything that you need. Thank you again, Serge, for being here. And I think there was one request we have seen in terms of the time for the installation. Again, I will get back to Anna and the Certara group to give us another time, because obviously we are in different time zones. For some of our participants, that is very late at night. So again, I would request Anna and the Sartara group to give us another time for installation. So we will resolve that for you. Any other concerns or questions, please let us know. And if you're having any issues with regards to uploading the homework assignments or any of that as well, do send us an email and one of us will resolve that for you. I acknowledge Serge. Thank you, Serge, for being here and generously sharing this information with all of us this morning. And thank you for all the time and effort that you're putting in terms of creating the homework assignments and preparing the slide decks and everything. And I also acknowledge all the group leaders who have been working tirelessly, giving your own personal time to make sure that your group members have worked on the homework assignments. I know you have been meeting with your groups, as well as the group leaders are having their own meetings too, to be able to understand and address the homework questions. Again, I understand that these questions are a little maybe overreach, but our intention is to prepare you and also, give you, this is just, I would say, tip of the iceberg. There is a lot more in pharmacometrics and PKPD modeling. We could only cover so much in a 3-month period. So again, and also, of course, I acknowledge Project Dontabhaktuni team who have been working on the various aspects, sending you emails, staying in touch with you, and also some of them are group heads. So thank you so much for all the work that you're putting in. And thank you, Rajan, for all the support. Again, anything comes up during this time, please send us an email and we are here to help you out. Serge, any closing remarks from your end?
No, it was really a pleasure to be a part of this adventure. I think that's something that we should do more often and different topics. And again, if anybody has an issue with the homework, you can send a request to Aruna and she will come to me. Again, my goal is really to help you, and certainly not to be in a situation where you are not able to do the homework. Then I just want you to just think a little bit. And I think that I gave you some advice that should really help you to do all the homework. Again, not to do the likelihood homework. Aruna, I told you that about the likelihood homework, it's off. And it's off. And all the other one you should try to do as much as possible. And it was really a pleasure. I will continue to be up to the end because I'm interested to be a part of this NLME because I'm an expert in Phoenix and NLME. Then I still will be hopefully a friend.
So in preparation for the R for Pharmacometrics, we will send you some details because you will have to install R. Again, Rajan will tell you more details about it. And we will send you the email, how to install. We will start with the basics of R. You don't need to have any background knowledge or information. And looking forward to moving on to the Mod 2 or the Module 2 of our workshop here. You do have time up until next Friday to complete all your homework assignments so far. Some of the assignment answers have already been discussed. that's absolutely fine. I would love for you to actually take the time and complete the assignments. And of course, there is one more assignment for which we have not addressed the answers yet. And next week, when Sir joins us after Dr. Rajan's workshop, we will go over those assignment answers. And if you have any questions, you can ask them then or ask over the email. Thank you, everyone. Thank you for being here. And we look forward to seeing you on Part 2 of our workshop. Have a great day.
Thank you, everybody. Bye-bye.
Bye.
Thank you, Serge. Thank you, Aruna.
Thank you.